So in this video, we're going to start applying Newton's second law, and we are going to do this for two types of problems. One is equilibrium problems, right? And in these problems, the net force is equal to zero, and the object is not moving. All the forces cancel each other. And the second problem is problems where there is a net force, right? So net force is not equal to zero, and then the object is accelerating. The acceleration is not equal to zero. Let's start with equilibrium. And so these are objects that are not moving, and there are two types of equilibrium. Is when the velocity is equal to zero or when the velocity is equal to a constant. So those two cases are equilibrium. So basically the acceleration is equal to zero, delta V is equal to zero, velocity is not changing. So those are the two types of equilibrium. So we call the first one statics, when the velocity is equal to zero, and the second one dynamics. So the net force is equal to zero, and therefore Newton's second law becomes the sum of the forces are equal to zero. And so, because we have two possible coordinates, x and y, so we are going to have two set of Newton's law, because there is one for the y coordinate and one for the x coordinate, right? So remember, a vector has two components in 2D, has an x and a y component, right? And so therefore, Newton's second law is a vector equation. So this Newton's second law is actually two equations, one for the x and one for the y. So let's do this by looking at one problem, right? So let's go through the steps. Remember, first you strategize, you draw a picture, you prepare, so you make sure that you understand your problem. Then after your picture, you also write what you know and what you need to find. Then you write two equations, one for the x and one for the y axis, right? So you're going to set your coordinate system and write two equations, and then you're going to solve these equations. So the best way to look at all these problems is to look at all these steps is to look at one problem. So we have a monkey here hanging, and so the monkey is 500 newtons, that's the weight. And it hangs from this vertical rope. And the question is, what is the tension on the rope? And that's a question that you would want to know if you want to know if the rope is going to break and the monkey is going to fall or things like that. So this is a problem in statics equilibrium, and so the net force is zero. So let's look at the steps. The first thing is a free body diagram. So we draw our coordinate system, x and y, and then we draw the two forces. We have the weight and we have the tension. That's the two forces. And so this is a static equilibrium, so the net force is equal to zero. That's Newton's second law. So there will be two equations here, one for the x and one for the y, but there's nothing happening in the x-axis, so all we have to look at is the equation for the y coordinate. So here's the equation for the y coordinate. The tension is equal to the weight. So now we can solve here, and this is equal to zero because there's no acceleration. So we can solve for the tension here, and we find that the tension is equal to 500 newtons. So that's the simplest problem you can solve. So let's look at a more complicated problem here. So we have a car that is being pulled by this rope at an angle of 20 degrees. You're given the mass of the car, you're given the angle. You're being told that the car is moving at a steady speed. That means the acceleration is equal to zero. This is a dynamic equilibrium problem. A friction of 320 newtons is applied to the car and opposes the motion. So what is the tension again? What is the tension on the rope? So we draw a picture. That's usually our first step, and we write what we know and what we need to find. We know the angle, the mass, the friction. We need to find the tension. So let's draw a free body diagram. This is our free body diagram here. We have the tension, we have the normal force, we have the weight on the car, and we have the friction applied. So those are the four forces, right? And now we write two equations. So remember, so we have an x and a y coordinate, right? So we have two equations, one for the x and one for the y. This is the equation for the x coordinate. This is the equation for the y coordinate. The x component of the normal plus the x component of the tension plus the x component of the friction plus the x component of the weight is equal to 0. And same for the y component. So here is a table. You don't need to do any of this when you solve problems, but here is just a nice way to show it to you. So I'm going to redraw the free body diagram. We have tension, we have weight, we have normal force, and we have friction. And all these are vectors. And this angle here is 20 degrees. So normal force has two components, right? Nx and Nx and Ny. However, the component in x for the normal force is 0, so the only one that survives is Ny. So the tension have two components, t cosine theta, the x component, and then t sine theta, which is the y component. The friction has only one component, which is in the x component, minus F, and the weight has two components, has one component in the y direction. So then these two equations here, they reduce to this. For the x component is t cosine theta minus the friction is equal to 0. And for the y component is normal plus t sine theta minus the weight is equal to 0. So the first equation actually would allow us to solve for our solution here. So we get t, which is what we want, is the friction divided by cosine theta, and so on. Then we get that the tension is 340 newtons, and this is our solution here. So the second type of problems that we want to solve using Newton's second law is dynamics problems. In these problems, the acceleration is no longer equal to 0, and there is an acceleration, and therefore there is a motion, right? There is a change in motion. Again, you're going to have two equations, one for the x and one for the y, right? And then you need to be able to solve these two equations. So remember, we need to draw a picture, draw a free body diagram, list our knowns and unknowns, write Newton's second law for x and y components, and solve them. So let's just look at how to do that. So we have a ball that is being kicked, and then it's moving. It moves from here all the way here, and in that process there is a friction acting on the ball. So we want to find the final position of the ball, right? So you have a 46 grams, and then the ball has an initial speed of 3 meters per second. There is a small friction of 0.02 newtons acting on the ball, and then so we want to know if the ball is going to go 10 meters. That is what we need. So basically we need to find this final position. That's what we need to find. So let's draw pictures here, all the pictures that we need. We have the acceleration here with the initial state, final state, and all the knowns and unknowns. We have initial position, initial velocity, final velocity is 0 because the ball is going to stop at the end. We have the friction, and we have the mass. We want to find the final position. Free body diagram, the most important thing. So we have normal force acting on the ball. We have the weight, and we have the friction and acting backward. What is the net force? Well, normal cancels the weight, and the only thing remaining is the friction, which is equal to the net force. So now we can write Newton's second law. We write two equations, one for the x and one for the y, right? So we simplify these two equations, and we realize that we only need to solve for the x component, right? So we find the acceleration x, which is minus 0.43 meters per second squared. It's a negative acceleration because the ball is slowing down. So this is what is left from your x equation. And now we can use our kinematics equations. So we have the acceleration. We want to find this guy. We know this guy. This is 0 because it stops, and we know this guy. So we can put everything in place, and we get that our final our ball goes 10.3 meters, so therefore it reaches the hole. So one more problem here. We'll go through this fairly quick. So we have the same car that we had before, but now we have acceleration. So we have initial, final state, but now the speed is going to be increasing. So this is a dynamic problem. So what are the things that we know? We know the initial position, initial velocity, the angle the tension is making, the mass, the friction. We know the final velocity now is going to be 12 meters per second, and the time when that happens is 10 seconds, right? So I never read the problem, so let's just read it first before. So we have a car with mass of 1,500 kilograms being towed by a rope at an angle of 20 degrees with the horizontal. There is a friction force. So what is the tension when the car reaches a velocity of 12 meters per second in 10 seconds? So this is our nice picture, free body diagram. So now we have tension, we have the normal force, the weight, and the friction. And notice the normal force is less than the weight, so they don't cancel completely, but there is this component of the tension that is helping the normal force cancel the weight. So now we go ahead and write Newton's equations. We have two equations, x and y. We can simplify them, right? So we have the x component of the weight minus the friction is equal to mass times acceleration, a normal force plus the y component of the weight minus the tension minus the weight is equal to 0. So we want to find the tension, so we only need to use the first equation. We use that. So, but we need the acceleration. For that, we use the change in velocity divided by the time, which is 12 meters per second minus 0 divided by 10 seconds. So that is the acceleration. And now we can use that acceleration here to find the tension. And the tension is 2,300 newtons.